Warehouse logistics using autonomous mobile robots is one of the most demanded industrial automation projects. The technology applied to this field is growing fast and spreading even faster. However, this kind of application is far from being fully resolved and faces new challenges every day. dCenter brings cutting-edge fog computing technology to improve the workflow of this use case. In this video will be shown the results and benefits of applying dCenter features to robotic logistics. The technology provided by dCenter is wide, so it's important to highlight the components used here. From the cloud infrastructure we will use infrastructure management, the orchestrator, security, and SLA. The microservices used are AI packages, and cross-border data management. The specific key points of innovation demonstrated in this use case are detecting a human or robot by camera with a confidence greater than 90%. Detecting accurately the position of obstacles with less than 20 mm of tolerance. Reduce the robot's CPU computation saturation at least by 10%. Now let's present the type of devices. In the robotic logistic use case there are two main types of devices: pure computing nodes, and mobile nodes. The pure computing nodes will be non-moving nodes, used to bear the load of the most critical and resource-hungry software. These devices will act as Kubernetes nodes on the edge region. The edge devices will be x86-64 machines connected via a wired interface with higher resources. On the software side, they will run among others, the following key microservices: dCenter Container Orchestrator, Fog Atlas App Composer, Topology Dashboard, AI Object Recognition, and the Fleet Management System. Mobile nodes will be Robotics RB1 base. These are commercial autonomous mobile robots designed for indoor warehouse logistics or research. The equipment includes high mobility differential drive, automated payload lift that allows them to transport up to 50 kilograms, a laser range finder that will allow the robot to detect nearby objects and stop in a safe distance, a RGBD camera that will allow him to take photographs of the objects found in its front, multicolor lights and buzzers to indicate the status of the robot, alert a person or indicate the object detection. Low-power x86-64 computers. The software required by the robot has been containerized and splitted by function in order to allow offloading. All robots will be part of the Kubernetes cluster using a wireless interface, but each one will be in a different region. Now the smart path planning using AI object recognition will be presented. The AI provided by dCenter will improve the warehouse workflow, increasing the efficiency of the system. The fleet manager system will ask the robot to grab a cart at the pick point and bring it to the designated place point. In the demonstration warehouse layout, there will be unique pick and place points, and two routes available between them, an optimal and alternative path. The route planning will always try to optimize the moving and transportation time, so it will try to make the robot use the main path whenever possible. The optimal route will be blocked by different obstacles, and the fleet management system will make a smart decision using the information provided by the AI. The object recognition confidence level KPI will be shown in this section. As a control scenario, the robot will move the cart with the optimal route unblocked. This will be used to compare the behavior of the system when an obstacle appears. When the robot is on a mission, the lights will turn white and start a swipe animation. The robot is performing the cart approach maneuver, in order to position itself below it. Next, the elevator will rise for picking up the cart. The upper left camera shows in detail the picking point. The upper right camera provides a clear view of the last part of the alternative route. On the lower left camera the placing point is shown. On the lower right camera, a clear view of the first part of the alternative route can be seen. On the center left, shows the internal robot variables, such as localization, goals and laser points. Finally, the robot camera is on the center right. Leaving the cart on the designated place, is the inverse of the picking operation. First, the elevator is lowered to place the cart. Next, the robot will turn, and move away from the goods. Now the optimal path is blocked by a person. The robot will stop due to the presence of an unexpected object. A picture will be sent to AI and it will recognize a person there. The robot is commanded to emit light and sound alerts, so the worker can clear the path. Notice that, when a person will be identified, the robot lights turn to blinking red. As the result of the training, the worker boot is highlighted on the image as a person with a confidence greater than 90%. Before using Decenter, this robot would stay silent and wait till the person moves without alerting its presence. With this new type of information from the environment, more complex behaviors might be implemented. When another robot is on the optimal path, again, the movement will stop. When the AI returns the recognition as a robot, a temporary reroute to the alternative path will be done. If the secondary robot clears the path, the loaded vehicle will use the optimal path to place the goods. The lights will blink blue when the AI detects another robot in the image. The robot is spotlighted with a confidence superior to the 90% as the KPI demanded. This way of detecting other machines can be applied in mixed environments where heterogeneous automated or semi-automated devices can block temporarily the alleys. This is especially interesting in a high dynamic environment where fixed automation will require a constant reprogramming of the rules. The behavior of this robot is closer to a human worker, who sees the path blocked and smartly uses an alternative route. Finally, the optimal path will be blocked by a non-mobile object, in this case, a wooden box. Now the AI won't be able to recognize this object, and it will be treated as a permanent block on this point. The path will be blocked for all robots and the picking and placing will be done using the alternative route. The robot will indicate that it has found an unknown obstacle using blinking yellow lights. Even though in this case, the new information is really useful to the fleet management system. It has an image, the position and time of the found object, and it might communicate with the maintenance team in order to remove the obstacle. The position estimation of the object in front of the robot is crucial to stop the robot before a possible collision and also to know if the object is in the path of the robot or not. To compare the measure calculated by the system and the real one, random objects were placed in front of the robot at different distances. For each test, the value returned by the estimation position algorithm is compared with the real measure taken by hand. The maximum average value of the error is 6 mm in the worst case, but the total average error is 0.2 mm. The standard deviation error per each distance has been also plotted. In conclusion, the standard deviation error resulting is 15.7 mm, so it can be concluded that the measurement estimation is below 20 mm as was dictated for this KPI. One of the most interesting features of Decenter for robotics applications is offloading. As it said before, the robotic software is divided into several containers. This software is orchestrated by Kubernetes using a special fog operator that allows smart placing the load among different regions. That's specially relevant due to the battery-powered nature of the robots. compromises had to be made in order to reach a good balance between performance and runtime. With Decenter, we can place computation load to edge devices or idle robots, so it's possible to run resource-hungry algorithms and save battery on the same time. In this context, vertical offloading means to delegate the computation to the edge region, where the machines are powered by the electric grid, and they have more resources. In this graph is shown that before the offloading, the robot uses about 2000 milli-CPUs. When the offloading is done, the usage drops to around 1400 milli-CPUs. That's greater than 30% of CPU saving, and the robot software capabilities remain the same. On the other side, horizontal offloading means to delegate computation to another robot. This is especially relevant when there are a great number of robots. Charging or idle robots can take the computational load from others because they are not using all their resources. In the graph it is shown that before the offloading, Robot 1 uses around 2000 milli-CPUs, and Robot 2 around 750 milli-CPUs because it is in idle state. When the offloading is performed, the Robot 1 CPU drops to around 1400 milli-CPUs, and the Robot 2 reaches around 1800 milli-CPUs. The CPU saturation is reduced by more than 30%. In both cases, the CPU saturation decrease KPI of 10% is more than achieved. We are going to highlight the benefits of Decenter by comparing the Robotic Logistics use case before and after applying it. Before, the robot software ran on bare metal. Now, the software runs in containers. That brings a more homogeneous deployments and the ability to update over the air or perform a rollback easily. Before, the robot could only run its own processors. Now, these processors can be placed over the idle robots or even into the edge device. That reduces the use of computational resources and allows the robot to achieve longer runtime periods without recharging the battery. Before, if an AI was wanted to be used, it must have been implemented and trained by the robotic provider. Now, AI packages and models are available from a repository, which allows us to use different training sets or recognition algorithms effortlessly. Before, when a robot finds something blocking in its way, it wasn't able to recognize the type of object it was. The only possible action was to wait until the path became free again. Now, using AI, it's capable of distinguishing among an unknown obstacle, a person or another robot. With this information, the Fleet Manager system makes a smart decision in each case, including rerouting to an alternative path, alerting a human to move away, or blocking this path to other robots. All these features improve notably the warehouse efficiency. Thanks for watching. For more information, visit the Decenter project website, www.decenter-project.eu.